His advisor is Dr. Jannick Rolland. He worked in the area of freeform optics, optical design. He's interested in optical engineering. And he has won the Michael Kidger Memorial Scholarship, as also he has won the Code 5 Synopsys optical design competition. With this, let us welcome Dr. Takaki.
Hello. Thank you for the introduction. Yeah, so I'm Nick Takaki, and today I'm going to be, well, the talk is titled Mathematical Surface Descriptions in Freeform Optical Design. I did realize as I was looking over my slides that I've actually replaced most of the equations with pictures. So apologies for that in advance, but if you want some equations, talk to me afterwards. I'll send you some papers. Anyway, it's great to be given the opportunity to talk here, and so I'll dive into it. I'll start off by just talking a bit about me. So as Professor Sasian mentioned, I finished my Ph.D. in optics in 2021 from the U of R. I worked with Professor Jannick Rolland on freeform optical design and things like mathematical surface descriptions. And hand in hand with that, my view into freeform is definitely a little bit U of R centric. So I've done my best to correct that bias, but if it looks like that's where the background I'm coming from, it definitely is. There's a lot of great work that's being done all over the place, and I wouldn't want to omit anything intentionally. That being said, my work was funded largely through the Center for Freeform Optics. This is a university industry cooperative research center, so this is where we take a whole bunch of companies like Synopsys and partner them with universities, both the University of Rochester and also the University of North Carolina at Charlotte, and that is where a lot of the work that I did in my PhD was funded through, and it was a great opportunity. Since graduating, though, I've joined Synopsys. I'm now on the Code 5 development team, adding features and fixing bugs in Code 5, and I'm having a great time. So that's me. I guess that means next I have to define what a freeform surface is. We could potentially have a bunch of definitions, but the one that I'm going to use here pulls from this optical review paper by Rolland et al., where freeform surfaces are defined as surfaces that have no axis of rotational invariance, either within the part or beyond it. And so what this is essentially it's a negative definition, and broadly speaking, it means that we're talking about it's not a sphere or a conic, not an axisymmetric optical A-sphere, and it is not an off-axis section of a conic or an axisymmetric A-sphere. So within the space that kind of carves out, though, there are a lot of different surfaces that could fit in. So I'd like to go next to look at a couple of different examples and why you might use them. We'll start off by looking at this, which is an example of an Alvarez lens. And the idea of an Alvarez lens is it's actually two freeform surfaces that are partnered with each other such that when they're kind of stacked up, perfectly aligned, they're not going to impart any optical power. But because of how these surfaces are described, if you shear them relative to each other, so you move them horizontally relative to each other, the system gains a focal length. So what this enables you to do is to have an optical zoom in your system without having a zooming group that goes forward and back. Instead, you have lateral shearing. This particular graphic comes from an Optics Express paper in 2015 by Zhu et al., and I chose it both for the reference, but also because if you look at this graphic, you can really see that these are not spheres or axisymmetric. You can really see what kind of we mean when we talk about freeform a little bit. But the original Alvarez lens patent, I believe, is from Alvarez and Humphrey in 1970. So this is one example of a freeform. The next example of a freeform I've pulled from this patent by Professor Hua's group here at University of Arizona. So the idea of this is that here we're using a freeform prism as a combiner in an AR/VR glasses application. So the idea is that this prism here would kind of sit in front of your eye like this, and the purpose is that you can both see through it, and also the prism can put an image of a microdisplay overlaid onto reality. So that's the AR/VR part of it. And in this case, each of the surfaces in a design architecture like this are going to be potentially highly complicated freeform surfaces with lots of degrees of freedom in order to achieve the performance you need in a system that has that shape. So that's another case where your freeform surfaces are present and the kind of designs they can enable. The last example, though, is one that is, I think, a little bit closer to the design example that I'll be talking about later on in this presentation, and that is the task of unobscured imaging systems. So in this case, an unobscured IR telescope. At a high level, the idea is that, if you think of a traditional reflective telescope, say a Ritchie-Chrétien, light comes in, hits the primary mirror, reflects back. Now it's got to hit something else, and that something else is going to be in the way of the incoming light in the first place. So one thing you might try to do is you might try to shift and rearrange your geometry so that the path of light gets out of the way of the mirrors. And when you do that, you might decide that you want to reach for freeform surfaces to facilitate your geometry, or maybe improve your optical performance, or reduce your package volume, and so on. And this particular telescope was fabricated in 2016 at UNC Charlotte as part of CFO. So here are some examples of freeform surfaces, just to sort of present that. Right, okay, so the question is, what about this is unobscured? Or, so I don't have a side geometry of this particular one, so we'll just have to use this one. But the idea here is that your light is going to sort of come in through here, hit the gold mirror. I believe the path is this one to that one. I might have those backwards, but the light is going to be bouncing between the mirrors, and because of the way that it's folded and tilted, you're not ever going to have the beam go back over across itself. So this is in contrast to if you have like a primary here and then your secondary is here, your light's gonna get blocked by that secondary. Thank you. Anyway, so yeah. So just some examples of what we mean when we talk about freeform surfaces. Before getting too far into it, though, I do want to remark that freeform surfaces are not necessarily new. We've been intentionally making freeform surfaces for quite some time. In prepping for this talk, I found some mention of examples of actually anamorphic lenses that might have been used in periscopes in tanks in World War I. So that would satisfy our definition of being a freeform, and it would quite predate even this example that's shown here. But I am going to kind of go with this example because it's at least more familiar to me. And what this is the Polaroid SX70 camera. So the idea of this camera, you might have seen it. It was widely popular. It could fold out, and you could look through, and you could take a picture, and then it would print out. They made they made a whole lot of these things, millions of them, starting in 1972, and it was hugely popular. It was popular, including with people like Andy Warhol here, who is featured taking a picture, I guess, of himself with his Polaroid SX70 camera. And believe it or not, the viewfinder in this featured not one but two freeform surfaces. The freeform surfaces were present in order to handle the sorts of things that we've been talking about here, which is to handle a system that has been tilted, in this case to enable its use as a viewfinder. But if you look at those two surfaces that have been expanded out there, we can see surface shapes that are not your traditional sphere or conic or what have you, and indeed those SAG profiles would be sort of familiar to me in a modern context as what I would definitely consider to be freeform. Only this rather predates the work that I'm doing. So it's important to remember that everything we do has a long history that can go back even further than we might expect, and that's no different for freeform than it is for anything else. That said, it is an exciting time to be in the freeform space. There's lots of progress that is happening, and it is continuing to develop really rapidly and exciting. So this is both in terms of things like improvements in manufacturing technology. On the left-hand side, you can see the bonnet polishing by Zico and MRF technology by QED. These sorts of technologies have been used to facilitate the fabrication of freeform imaging systems, some examples of which are included there in the middle. But there are many more out there. And of course, hand in hand with improvements in fabrication technology, we've also seen improvements in metrology technology, because if you can't measure it, you can't really produce it effectively. So the ultrasurf is an example of a metrology technique that you might use for freeform. And honestly, as sort of an example of how quickly things are developing, you'll notice that a lot of the systems that are showing here are from the 2010s. I would be able to replace all of these pictures with things that have happened, since 2019, and would not have trouble filling this presentation. So things really are continuing to evolve and develop, and it's an exciting time to be in freeform. That being said, challenges still remain, and one of those challenges is the fact that null tests for freeform surfaces are going to potentially be more complicated, require more specialized equipment and technology than for your traditional optics. So here on the left-hand side is a simulated freeform interferogram for mirror 2 of the telescope Pathfinder 1. So Pathfinder 1 was it's shown on the previous slide. It's also shown here in the bottom right. That simulated interferogram corresponds to about 120 microns of PV sag departure. And first back at all, they were able to interferometrically test this surface, which was a really great achievement, especially in that context. But to do that, it involved tilting during the test, it involved an off or null, it involved a deformable mirror, all of which is to show that in order to test freeform surfaces like this, you might need to find yourself reaching for specialized techniques. And the fact that this was successful is a testament to the work that was done, but it also shows how things can get complicated. And this is only 120 microns of departures. Departures can be even greater. The test can be even more complex. And what that leads to is my sort of thesis here, which is that there is a need to think about your test during your design. And specifically, I'm thinking about interferometric tests. So, with that underway, we'll next switch to a question. Can conics help? And I would say yes, they can. Conical optics are optical surfaces that are based on conic sections. So these are your spheres, your ellipses, your parabolas, and your hyperbolas. Conical optics have a long history in a long history in optics in general. And they have a lot of useful properties. One property that's particularly relevant today is that most conical optics can perfectly image one specific focus to the other focus. I have chosen to exclude oblate ellipses there, but even that exclusion is not totally necessary because an oblate ellipse is able to do stigmatic imaging in 2D, but in full 3D we can say that most conical optics are able to do the stigmatic imaging there as well. On top of this, off-axis sections of conics are a good starting point for freeform surfaces in your freeform designs. And before getting too far into that, what I mean by off-axis is essentially as follows. So here we have a section of an ellipse that's in black. The red dotted line is the axis of the ellipse. So if you wanted to turn this into an optical surface, you would spin around that red dotted line. That's the axis of revolution. This ellipse has two sections shown on it. The first section is traced out by the red ray fan. This red ray fan is centered about the axis, so that would be the on-axis section of this ellipse. The blue ray fan, on the other hand, traces out a section that is away from that axis of revolution, and so that's what I mean when I talk about off-axis sections of ellipse, or conics in general. So that's off-axis, and these off-axis conics have been useful as starting points in freeform. The conics also provide us some advantages when we're talking about null tests, because there are simple null tests available for each conic. The pictures that we show on the right-hand side are some examples of these Hindle tests from Optical Shop Testing by Malakara. And basically the idea here is that you leverage the stigmatic imaging properties of the conics in order to create your null test. When it comes to freeforms, the advantage happens, which is that a freeform surface that is close to being a conic can be tested in a similar fashion. If you're close to a conic, then you are going to be close to being stigmatic, and so you might be able to perform a test like this with resolvable fringes, and in that sense perform your interferometric test. You'll also notice that in many of these cases, there is a hole in the reference surface in order to facilitate the test. But when we're talking about off-axis sections, we may not even need to have that hole there because the off-axis sections may obviate the need for the hole that's present. And to give an example of what a test might look like, I'm going to go to this slide. So this is a slide from actually one of my colleagues at University of Rochester. He's now at NASA, so this slide is credit to Dr. John Papa. And what he was trying to do here is he was trying to take an off-axis section of something like an ellipse and align it by leveraging the stigmatic image properties. So in the bottom left, you have a Code 5 simulation of the setup that we're talking about here. Converging light comes in from the left-hand side, converges down to the first focus, hits the ellipse, goes to the second focus, hits the autoreflector and auto-reflecting sphere down there at the bottom, and then it goes back and forms the test. And these are the fringe patterns that he was recording during this alignment situation. And so what ends up happening here is that if your system is not perfectly aligned, so if you have displacement, you'll get the aberrations patterns that are shown across the top. You get different forms of astigmatism for X and Y displacement. You get coma for Z displacement. But if everything goes well and you get it aligned, then you don't see those fringe patterns, and instead you see what is shown here. So this, again, this is work that I had the pleasure of learning about through working with Dr. Papa, but I think it serves as a good example of what we're potentially trying to do when we're talking about testing these off-axis sections or testing freeforms that are close to these off-axis sections. So yeah, off-axis conics are very helpful in freeform design. And I want to stress also that really I'm not by any means the first person to reach this conclusion. There's a whole lot of work that other people have done, including some people here in this room, in the topic of using off-axis conics for freeform optical design. The citations here are by no means exclusive. I could have put many more on this slide, but the overall point is that you know, I'm coming from a very rich tradition here that I've gotten to take advantage of. So off-axis conics are gonna be helpful. That underway, we'll switch to our describing of our freeform optics. So this is the section where I took out all the math and replaced them with pictures. Here's an example of what I mean. So for the context of this presentation, when I talk about freeform surfaces, I'm going to be thinking about them in the context of a surface that can be described as a conventional base surface with extra degrees of freedom added on top. So as an example, if we look at that telescope from earlier in this presentation, if we zoom in on the mirror there, then that mirror could be described as a conventional base surface, so perhaps a sphere, which is what it is in this case, with added freeform departure terms on top. So these are potentially Zernike polynomial terms. This separation is useful for a couple of reasons, but mostly because it allows us to think about the base surface and freeform departure and the things that these contributions are doing separately. So for example, the base surface could give us intuition about the optical properties of the surface. For example, it may suggest to us what the first order properties are. And if our base surface is well chosen, it may suggest a fabrication or metrology regime. On the other hand, if we split things up into base surface and freeform departures and do a good job of it, the freeform departure terms are going to be useful from an aberration correction perspective. And they're going to be useful because they tend to drive your interferometric testability, at least if some caveats apply. So you know, your caveats include that you need to have a base surface that's null testable, and really when we're talking about reducing departures, it's sort of in an all else being equal type situation. And I definitely don't want to say that this is the only thing that matters, because as people who have to actually do the testing of these surfaces will tell you, it's a lot more complicated than just one number. But even so, separating it out into base surface and freeform departure can be useful because all else being equal, bigger departures may be harder to test. And so our goal is to try not to go too crazy with the freeforms. And that's pretty much exactly what our goal is going to be today. We want to achieve our design goals, so achieve suitable optical performance, while using minimal freeform departures. Those freeform departures are going to be described with Zernike polynomials. Each of those polynomials is going to have known aberration contributions, and we are going to use those aberration contributions to tell us, based on the aberrations present in our system, which terms we need to introduce and when. This design approach, again, is not something that I'm pioneering. It is instead something that I've learned from people like Dr. Bauer and Dr. Firschbach at U of R, and that tradition goes back and has its own history as well. But the point of by doing that is by being careful about how we introduce our freeform degrees of freedom to match them with the aberration needs of our system, we can minimize the freeform contributions that we add and not have, unnecessarily large departures. So that's our overall goal. And in this presentation, the goal of reducing those departures is going to be achieved by taking advantage of base off-axis conics. Specifically, what we're going to do is we are going to use our off-axis conics to remove the need for certain low-order polynomial terms. So specifically, we are going to take our freeform surfaces and we are going to remove the need for surface astigmatism and surface coma terms, so things like Z5, Z6, and Z7, Z8. By using the base off-axis conic, that off-axis conic is still null testable. So even though the surface is more complicated and has more aberration correction potential than a base sphere, we can still null it out using the Hindle test that we talked about before. And having done all that, it means that the sag departures that are left over afterwards are only going to be what is needed to achieve correction beyond the base off-axis conic parameters. And in that fashion, we are hopefully going to be able to reduce our departures. So that's the goal. Before getting too far into it, though, I do want to pause and talk a little bit about how we describe the off-axis conic, because there are a couple of different approaches that you could take. The first question is how we parameterize it. What numbers are you going to use to describe your off-axis conic? And what we're going to do is the following approach. So we describe our off-axis conic first by specifying the radius of curvature r and conic constant k of the parent. And then we're going to specify how far off-axis we go via the off-axis angle omega. And this off-axis angle omega is the angle that is formed by the off-axis surface normal and the axis of the parent z. So if you look at this picture here, the off-axis or the conic as a whole is in black. The blue rays trace out your off-axis segment. At the center of that off-axis segment, there's a blue arrow. That's the surface normal at the center of the off-axis segment. That's z tilde. And that z tilde is going to form an angle with the dotted line, which is your axis of revolution, the dotted red line. And that angle omega is going to be how we specify the off-axis segment that we're specifically using. This is an approach that I believe is started by Cardano and Núñez et al. In 1986, but it's also been implemented in Code 5 in the extended fringe Cerner key polynomials and Q2D freeform A-spheres in Code 5. And one of the reasons we're going to use this formulation is because it grants access, smooth and easy access to maximally off-axis ellipses. So what I mean by maximally off-axis ellipse is essentially in the red box over there on the right-hand side, you have the on-axis part. That would be omega equals 0. As you increase omega, you're getting further and further off-axis. But an ellipse, it's connected. So if you keep increasing that off-axis angle, eventually you're going to end up on the other side. And in that sense, you're back to being on-axis again, just on the other side. So the furthest away from the axis you can get is this blue box, which occurs at omega equals 90 degrees. That's your maximally off-axis ellipse. That's the section of the surface that I want smooth and easy access to. The reason I want smooth and easy access to that is because maximally off-axis ellipses differ from spheres primarily in terms of surface astigmatism. It's not exactly the same as surface astigmatism, but that's going to be the biggest difference. And in particular, the maximally off-axis ellipse is going to be fully plane symmetric, and so it's going to have no coma contributions. So what that means is that if we use off-axis ellipses as a design degree of freedom, we can isolate the surface astigmatism contributions from the surface coma contributions, which is going to be necessary for our design process. The last thing to talk about in terms of specifying the off-axis conic is how we talk about its power. There are a lot of variables that might be related to something like power for an off-axis conic. You could talk about the parent's radius of curvature r. Might not be that related to the power of the off-axis segment, but it is a term that you could think is related to power. You could also look at the in-plane or out-of-plane radii of curvature at the segment. Again, these are things that are somewhat related to the power of the conic and could be used. But we're not going to use them. Instead, we're going to be using the effective curvature, which is something that was sort of is the multiplicative average of the in-plane and out-of-plane radii of curvature. In a mathematical sense, the effective curvature is defined as 1 over the signed square root of the Gaussian curvature. And the reason that we're going to use this is because if you take this effective curvature and you plug it into Coddington's equations for an off-axis conic and its foci, then what you get, or what Schieser et al. Showed, is that the effective curvature satisfies this equation here. So 1 over Li plus 1 over Lo equals 2 over R effective, which rather resembles the equation for paraxial power. So we're going to be using this as our variable of control for when we're talking about trying to control the paraxial power of an off-axis conic. It's not exactly the same thing, but it is one parameter that we're using here, which we found to be successful. So we've defined our freeforms, we've defined our off-axis conics, we've talked about null tests. Let's now look at a motivating example for the comparison we're going to do. And the motivating example is a reflective prism. And our goal in looking at this motivating example is to try to understand how we can stay close to an off-axis conic. Earlier we talked about how if a freeform is close to an off-axis conic, then maybe you can still test it with a null test. But staying close, how do you do that? Do you follow your design process and then fit the surface at the end? Or do you design with off-axis conics from the start and achieve being close to an off-axis conic in that regard? And this motivating example will kind of do a quick and dirty run-through of the difference between fitting at the end and designing with off-axis conics from the start. So here's our brief motivating example. We're going to take this reflective prism. The two surfaces in the back, mirror 1 and mirror 2, these are both freeforms. We are going to look just at mirror 2, and we're going to be thinking about trying to fit this thing with off-axis conics and seeing what that can get you. Now, full disclosure, this probably isn't a great realistic example. You probably wouldn't test a system like this in this particular fashion for a lot of reasons, but this is the system that I was looking at when I started thinking about off-axis conics in this fashion, and it serves as a motivating example of what we mean, even if it isn't exactly relevant in this specific case. Anyway, we did our design process here. We tried our best to make sure we didn't have unnecessary freeform departures, but despite our best efforts, mirror 2 has the sag departure profiles shown there on the right-hand side. That heat map is showing the departures from the base sphere. So this is essentially what the Zernike freeform departures are. And it has 320 microns of PV sag departure. That's not great. We'd like to do better. And one thing that we might try is to take this sag departure profile and fit it with the best fit off-axis conic. And when we do that, we actually do get some reductions. This makes sense. The off-axis conic is a more complicated, more powerful surface than a base sphere, so fitting should reduce departures. And what we see is that we go from 320 microns of PV sag departure from base sphere to 130 microns of PV sag departure from best fit off-axis conic. That's a nice reduction, but if we look at the sag departure profile that remains, we can still see there is definitely some surface coma that is present, which is providing a lot of contributions. And we'd like to get rid of that. And so instead of fitting with the best fit off-axis conic at the end, what we're going to do is go back to the beginning of the design process and redesign using off-axis conics from the beginning, and we're going to completely eliminate the need for surface astigmatism and surface coma. And in that fashion, we end up with the departures from base off-axis conic that are shown there on the right-hand side, which is 12 microns of PV sag departure. That 10x reduction from even fitting with the base from the best fit off-axis conic was sort of exciting when I did this examination the first time. And while this example isn't necessarily the most practical, hopefully it serves as a motivation for why we're trying to look at this. So what are we going to do? We are going to redesign our systems with off-axis conics, and in so doing, we're going to eliminate the need for surface astigmatism and surface coma contributions. Instead, we are going to use the off-axis conic parameters in order to satisfy the aberration correction needs of these surface terms. It's important to note the off-axis conic is not exactly equivalent to the sphere plus astigmatism and coma, but what we're going to see is that we can nevertheless eliminate the need for them and create a new design with new freeform surfaces that are closer to the base off-axis conic. So that's our motivation, that's our approach. And with that, we'll go to the design example. For this talk, we're going to be re-examining Pathfinder 1. Pathfinder 1 is a 3-mirror telescope designed for use in the long-wave infrared. It was designed and in 2011, manufactured in 2014 by Borsbach et al. At the University of Rochester. And Pathfinder 1 achieves an RMS wavefront error over the field of 0.0085 waves at 10 microns. This is well below the diffraction limit, and we're going to be, for comparison's sake, we're going to be aiming for roughly equivalent performance. Here's the layout of Pathfinder 1, and I think this probably is a better example of what we mean when we talk about unobscured. We notice that the light coming in from the left-hand side is able to bounce around and hit all the mirrors without getting into anything being in the way. And another advantage of using Pathfinder 1 specifically is that this is, it's a well-known example in the freeform space, and the team at the U of R is able to build on all the lessons that were learned in creating this design in order to continue getting that progress and improvement today. So that's our design example, and what we're going to do is we're going to basically design this guy in 2 ways. On the left-hand side, we'll have our baseline design for comparison. This is going to use a base sphere. It's going to use Zernike polynomial terms on top of that, and it is going to include Zernike astigmatism and Zernike coma. At the end, we're going to fit the surfaces with the best fit off-axis conic, and we're going to look at the departures. Comparing against this, we are going to redesign this system with base off-axis conics from the start. We're still going to use Zernikes to describe our freeform departures, but we're going to exclude the Zernike astigmatism and Zernike coma terms. So they can't be present in the freeform departure part because those parameters simply aren't going to be used. So left-hand side is the baseline, right-hand side is what we're going to be testing. Both designs use the same starting point. What we do is we basically take something that has the same layout and first-order properties of Pathfinder 1, but has no freeform and so virtually no aberration correction at all. If you can kind of see the rays, it's not showing up super clearly on this one, but they're really not coming to a focus up there. This thing is severely limited in its initial performance, and that's how we like it because we're going to be trying to correct those aberrations. What we're going to do next is we're going to use full field displays to identify the initial limiting aberrations in the system. So a full field display is a way of looking at the aberrations in a system across the field. Each of these 4 diagrams is a separate full field display. Each symbol in the full field display corresponds to a point in the field. A bigger symbol represents greater aberrations, and for things like astigmatism and coma on the right-hand side, the orientation of the symbol corresponds to the balance between, or I guess the orientation of that aberration. So in this case, we see that we're starting off with 8.65 waves of RMS error, and that is almost entirely driven, or at least initially limited by the primary astigmatism that's shown here. This primary astigmatism is constant over the field, which so we're dealing with here is uniform field constant astigmatism. That's our initial limiting aberration, and that's what we want to start first. So if you remember our design approach, we have identified an aberration. We now want to introduce variables in order to correct this aberration. For the base sphere design, the correction approach is to introduce surface astigmatism terms on each mirror. So this would be your Z5, Z6. Technically only one of those since we're plane symmetric. Z5, I think. But we're going to be Otherwise, not really introducing anything else. In particular, we're going to leave the surface power fixed. We're going to leave the surface tilts and the surface spacings fixed. We're just going to be introducing our Zernike astigmatism term. Automatically, this isolates the surface astigmatism from other freeform departure terms, especially coma. And it has been shown that this is an approach you can take to correct your field constant astigmatism. On the right-hand side, though, is the off-axis conics. And if we recall, we don't have the Zernike astigmatism and Zernike coma terms. Instead, we are going to turn to the maximally off-axis ellipses that we talked about earlier. So what we're going to do is we are still going to constrain the geometry. We're still going to constrain the power of the off-axis conic by constraining R effective. And instead, then, what we're going to do is we're going to optimize the conic constant K and radius of curvature R at the parent for after we set omega to be 90 degrees. And if we recall, this guy is doubly plane symmetric and is primarily going to be giving us our surface astigmatism. It's not exactly equivalent, but that's what we're going to be doing. And if we look at how it works, we can see that things work pretty well. So here are full field displays of the aberration, the astigmatism aberration. On the left is our baseline design, which has been corrected using Zernike astigmatism terms. On the right is our full field display where we've done the correction using maximally off-axis ellipses. On the left-hand side, you've got about 4 waves of Zernike astigmatism remaining, and it is really not, the field constant astigmatism really has been nicely corrected. Remember, we started with 20, and now we're down to 4. And also, you can see that based on the orientation of the lines, that this is going to be a different field dependence than the earlier astigmatism. This is our field asymmetric field linear astigmatism. So that's the kind of correction that we would expect to see here, and it's what we achieve. On the right-hand side, though, we achieve is what we achieve using these maximally off-axis ellipses. And if we look at that, we can see that the shape is a little bit different. We don't have as clean of a correction of the field constant astigmatism, and in particular, we don't really see like a node as clearly as we do on the left-hand side. But if we look at the scale, and if we recall that we started with 20 waves, we can see that we have had some nice improvement. And in a lot of ways, we are very much in the same ballpark. So this astigmatism correction is not exactly equivalent, but it is comparable. And that's what we were hoping to see. So having corrected the astigmatism, we'll now look at the full field displays again, try to ask ourselves now what is limiting. We saw the field asymmetric field linear astigmatism on the previous slide, but on this one we can also see that one thing that's present is the primary coma, and that now is field constant. So this is going to be our limiting aberration, and we want to introduce variables to clean that guy up. So what do? Well, for the baseline design, the one with the base sphere, we're going to be introducing Zernike coma terms at and away from the stop in order to correct these aberrations. While on the right-hand side for the off-axis conic design, we are now going to release our use to use things other than maximally off-axis ellipses. So in particular, we're going to optimize this omega term and allow ourselves to drift away from maximally off-axis, which is going to start introducing things like surface coma, and in that fashion get our correction. And here we can see the results after performing this optimization. On the left-hand side, you can see the full field display of the coma. It has gone from, I believe, let's check, 6.7 waves maximum down to about half a wave of correction using Zernike astigmatism and Zernike coma. And moreover, if we look at the distribution of that coma, all the little coma arrows are pointing away from the center, and it's increasing as you go away from the center. So this is the aberration that remains is not field constant coma. That has been corrected, and instead what we're left behind with is essentially field symmetric coma. So what we might consider normal axisymmetric coma. So that's what's on the left-hand side. On the right-hand side, we see virtually the same thing. The scale is a little bit different, or sorry, the level of correction is a little bit different. On the right-hand side, we get only down to 0.7 waves, whereas on the left we have 0.56. But as with the case for astigmatism correction, we're definitely in the same ballpark, even if we're not exactly equivalent. After that, we have basically done what we need to do for leveraging the off-axis conic part. And from here on out, the approach is going to basically be the same for the two design examples. The next step in my design process here would be to notice, okay, so we're dealing with field symmetric aberrations, so we're going to introduce our rotationally invariant terms like Z9, Z16, so the A-sphere terms. We'll introduce them to both designs, and that will give us further correction. After that, we would then optimize the power in the base sphere design, which is the point at which we would release the effective curvature in the base off-axis conic design. But essentially, these steps are, again, equivalent. So our design process is the same for the benchmark as it is for the off-axis conic design, so we'll just skip to the end there. And here is the optical performance full field displays at the end. Both of these two designs achieve an RMS wavefront error of about 0.0085 waves at 10 microns. This is the goal that we were hoping to achieve. And if we look at the field, or at the performance over the field, we can see that while these two designs aren't exactly equivalent in terms of their optical performance, we achieve about the same level of field uniformity in the benchmark case as we do for the base off-axis conic design. So, all of which is to say, we've ended up with two designs that achieve, essentially approximately the same optical performance, and we hit the targets that we want. So that's great, but the real kicker, the real goal here was to reduce our freeform departures. So let's go ahead and look at those. Here are the freeform departures of the base sphere design, so our benchmark design, with departures reported from the base sphere. There's a lot of numbers on this slide, so I do want to just draw attention. Let's only look at the maximum sag departure, so the PV sag departure. That's not necessarily going to be a perfect metric in terms of your surface testability, but it serves as a good proxy to tell the story, so let's look at that. For mirror 1, we've got 26 microns of sag departure. Mirror 2 has 9 microns. Mirror 3 has 225 microns. So this is the sag departure that we're starting with for these three surfaces. This uses base spheres. So the next thing we're going to do is we're going to take these three sag departure profiles and we're going to fit them with the best fit off-axis conic afterwards. So the left-hand side shows the base sphere departures. The right-hand side shows the departure from the best fit off-axis conic. You get some improvement. Mirror 1 goes from 26 microns to 23. Mirror 2 goes from 9 to 8. Mirror 3 shows the best improvement from 225 microns down to 54 microns. This is roughly analogous to what we saw in our motivating example. It's nice, but just as in our motivating example, we still see things like surface coma that's present. This is especially true in Mirror 1 and Mirror 3. So we'll take our fit with best fit off-axis conic at the end design, and we will compare it with our off-axis conic redesign, and this is that comparison. So Mirror 1 had 23 microns in the fitting case, but with redesign we get down to 4 microns. For Mirror 2, 8 microns goes to 3. For Mirror 3, 54 microns goes down to 5. Moreover, we don't see any residual surface coma in the sag departure profiles. We didn't use it, so it shouldn't be there. But instead, we do see freeform departures that we would expect if those things had been removed. So we see things like Zernike trefoil terms, or secondary astigmatism, or spherical aberration, which is what we would expect. The last thing we're going to look at is we're just going to take these three surfaces in the best fit off-axis conic case, and we'll just simulate a null test and look at what some of the interferograms might look like. So these are simulated null tests. At the bottom, we have approximately the scale in terms of the number of waves, peak to valley, that you see. For Mirror 1, those 4 microns end up corresponding to about 32 waves in the null test. They're relatively evenly distributed across the pupil as well, so not too dense. Mirror 2, with only 3 microns, is the best case. It has 17 waves across the field, across the pupil. And then Mirror 3, which had 5 microns of PV sag departure, ends up having 35 waves. As you're looking at this, it does look like the fringes are washed out on this PowerPoint projector. I will say the resolution is higher in the simulation, and secondarily, the fringe density is higher for Mirror 3 than the other ones, but these fringes are, at least in principle, resolvable. And they're certainly a lot more resolvable than compared to, for example, the 250 microns that you might have had to get if you didn't introduce the off-axis conics. So this is what the simulated null tests might look like, and these null tests would be sort of like the standard Hindle ones that we were looking at in Malakala earlier. So in conclusion, we discussed freeforms both in my view of the present context and historically. We also discussed a design example that uses the base off-axis conics. We guided our aberration correction through the use of full field displays, and then we used off-axis conic parameters as driven via optimization in order to do our correction, and then we looked at the sag departures of the resulting designs. So those are the conclusions. Before wrapping up, though, I do want to talk a little bit about the places where a lot of this work was done. So a lot of my PhD research was funded through the Center for Freeform Optics, and I'm now at Synopsys. So since I see a lot of students in the room, and since we may be thinking about things other students are doing at U of R, I want to briefly talk about the center here. So the Center for Freeform Optics is it's this collaboration between universities and industry that is trying to basically advance the field of freeform optics and its adoption and its technologies. Here are a handful of representative publications of the kind of work that's being done through CFO. I just pulled them off the CFO's website. So you have things like talking about null tests for freeforms. On the top left, you have a Alvarez type design approach in the top right. In the bottom left, you have some work that was done in so-called metaform optics. So this is meta optics plus freeform. That's work that's being looked at. And in the bottom right, we have a CubeSat format freeform hyperspectral imager. So this is just kind of a snapshot of the work that's being done at CFO. Here's a snapshot of some of the industrial sponsors of CFO. And there is Synopsys, which is where I work now. So it's been really great to sort of come back as an industry advisor to the center. So anyway, that's just a little bit about them. And with that, I think we're done. So I'll open the floor to questions.